Hi everyone, thank you for joining us. I'm Trish McLean, the marketing person at Mirus, and we're happy to have people all over the world joining us today's webinar, which is Diagnosing Harmonics, Power Loss and Energy Savings Using SOLV. So this past spring we undertook some industry research that really showed how critical and valuable it is for engineers working in the industry to be able to diagnose current conditions and anticipate harmonics with the introduction of filters. And this is exactly what you're able to do with SOLV. So our presenter today is Mirus Farbish. Mirus graduated from Warsaw University of Technology in 1997 with a master's in electrical engineering with a specialty in power electronics. He was the design engineer for Medcom, AC and DC power solutions and traction converters in Warsaw, Poland. Medcom specializes in the design of power electronic converters. In 2002, Mirus immigrated to Canada, and in 2008, he joined Mirus International to provide his expertise on power electronics, power conversion technologies, and power quality issues. He is the Chief Applications and Power Electronics Engineer for Mirus, and we're very happy to have him with us today. A few logistics for today's webinar. Because we do have many people on the line, everyone's sound is muted. You can send in your questions via the questions section, and we'll be answering questions at the end of the presentation. The presentation will be about 30 minutes with questions to follow, and for all of those of you who require documentation to apply for professional development hours, please email us at mirusinternational.com, and we'll send you a certificate of participation and a test following the webinar. And with that, I'll hand it over to Mirus.
Thank you for joining us today on this session for using SOLV. In this webinar, we will demonstrate how SOLV 6.5 can help you identify harmonic problems, power losses, and diagnose energy saving solutions for your adjustable speed drive applications. Initially, I will do a quick introduction to user interface for those that are not proficient in SOLV, but this seminar was prepared to demonstrate features and report capabilities of this powerful tool. After the presentation, we'll have a brief Q&A session. SOLV 6.5, as its predecessors, is computer simulation software designed for harmonic analysis with adjustable speed drive applications. Main features include the ability to simulate voltage and current waveform distortion, ability to calculate harmonic spectrums, ability to calculate power losses and energy savings. Also the ability to run dual scenarios, which was a new feature introduced last year. Simple report generation. The simulation summary report combines several pages, the PDF document including one-line parameters, waveforms and spectrums, compliance reports and harmonic distortion reports. Also comparison and energy analysis report compares performance parameters for two simulations. We also brought back old individual report features on users' requests from old versions. Examples today, I will present the linear AUHF versus 8-impulse. We will demonstrate how 8-impulse drive performance drops off with even low levels of voltage imbalance and voltage distortion. We will show energy savings that can result when linear is used. And we will demonstrate influence of source impedance on harmonic distortion in generator versus utility applications, basically weak source and stiff source influence. So initially, we will start SOLV and set up the power system parameters for the simulation. So in the opening screen, we can select start a new simulation or open an existing saved simulation from previous analysis. So after selecting a new simulation, project information can be entered. So rather than type this now, I will click OK and demonstrate how to load an existing simulation file. from the top menu file, I can choose Open and load saved file with SOLV extension, and clicking Open, that project information appears again, and so I click OK, and we have active single line diagram. Let me switch to full screen so we see all better. You can save your file by selecting File and go Save or Save As. Other features on the main menu is Project, which allows for second scenario and changing operating info. Settings, which allows you to select between imperial or metric units for cable sizes and length. Run simulation button, and Help, where is the user guide. Other menu features are not active until we actually run the simulation. The simulation parameters can be entered in any order. In this example, I will begin with the source. So moving the cursor over a source symbol and clicking brings up the selection window for the source data. We can choose our system frequency, 60 or 50 Hertz, and apply pre-existing source conditions such as background voltage distortion and line voltage imbalance. At this time, I will not select any pre-existing conditions, so after choosing OK, after choosing the frequency, I am clicking OK, and moving the cursor on the right side to the utility transformer, we can select the generator or utility transformer. Moving the cursor above the line highlights the transformer, below the line highlights the generator. So with the utility transformer highlighted, left click opens the selection window with transformer ratings and system voltage. There are three ways to define the utility source. Most often you will enter transformer size, kVA, and percent impedance. But when this is unavailable, utility fault level in either MVA or short circuit current in kiloamps can be entered instead. For this simulation, I'm using short circuit current 2.5 kA and secondary voltage 13.8 kV. If the utility information is not available, simulation can be performed without entering the source information. To enter cable information, simply click the cable symbol and cable data can be entered. So I selected 300 feet and 2 gauge wire with number of one conductor per phase. When I click OK, this information appears on the single line. If we prefer to be working in metric cable sizes instead of imperial, this can be changed in settings and changing the setup to metric. You can see that cable size changed to millimeters square and length to meters. So now when I click the cable symbol, we have cable selections for meter sizes, and we can choose length in meters. Running a simulation without the cable information results in conservative value of current harmonics, so this is not always needed to be entered. Therefore, I remove that cable from this example. Power factor correction capacitors allow for entering capacitor banks and tuned reactors or detuning reactors for the particular bank. This is also not really required, but can be included if desired. Clicking on the user transformer brings up the dialog for the user transformer setup, and it's very similar to the utility transformer. so you can select the transformer in kVA and percent impedance, or fault level if that's unknown. Additionally, we have a section for efficiency and the current loss, that's in percent of the total losses for that particular transformer. Transformer efficiency is important for accurate energy analysis, so this is why we have this in this section. On the right side of the single line diagram, we have load information. The first branch is for linear load, and up to 9 non-linear loads can be defined. If linear loads are to be included in the simulation, we just click the first symbol, and we have power in kilowatts and displacement power factor, which can be defined as lagging or unity. Similarly, the variable frequency drive loads, when we click, the drive system input data window opens, and we can, this is where we can define the actual drive. Information can be entered in any order, but let's start with the motor rating in horsepower or kilowatts in the motor section here. Since SOLV uses built-in models for filters and drives in relation to the motor rating, the motor horsepower or kilowatt size must be selected from the pull-down list. So I'm selecting 900 horsepower, and then we can select the desired load level in percent. Normally simulations will be done at full load, since that is the highest levels of harmonic voltage distortion, but any other value for load level can be entered. So I'm using default 100% load. In the drive system, we have choice of 7 different types of nonlinear VFD loads. Simple 6-pulse VFD, 6-pulse VFD with the lineator advanced universal harmonic filter, 3 types of multi-pulse VFDs, 12, 18, and 24 pulse, thyristor control DC drive, and DC drive with the lineator UHF. To demonstrate that the use of simple 6-pulse VFD will often result in harmonic distortion that will not meet recommended standards such as IEEE 519, our first simulation will be VFD only with the input AC reactor. Many VFDs actually come equipped with either AC input reactor or a DC link choke. So we can define this in the section for the input AC reactor or DC link reactor here. This can be described as percent impedance or actual inductance in millihenry value. Next is the DC smoothing capacitor for the VFD. This can be changed, but normally the default value is used. Cable, to enter information for the cable, just we click that button, and as before we can enter the cable run in cable size and number of conductors per phase. Also drive transformer, we click the drive transformer rating, but for this example I will not select any branch transformer. Last field on the drive system input data is the for short comments, but I leave that empty for now. Once our loads are defined, we can click OK and just run the simulation. And depending on the model complexity, this may take a few seconds. This time it was quick, but sometimes when the system is defined with many different nonlinear loads, it takes a little bit longer. After the calculation has finished, simulation results are on the one-line diagram at each load branch. Also shown in the table here for distribution panel, user transformer secondary, which is defined as PCC1, and utility transformer secondary, which is defined as PCC number 2. You can see current distortion at the VFD load branch is above 29%, and the voltage distortion at the user transformer is 6.8%. But the true power of SOLV is in the extensive information available for analysis after this calculation. So let's begin with waveform and spectrum graphs. So when you click on the top menu for waveform and spectrum and select PCC number 2, we can see waveforms and spectrums window open, and moving the cursor in the area of the harmonic spectrum, you can see the selection hand appears. This usually indicates that this is area where you can click. So by clicking here, another window opens with the individual harmonic distortion results, and this can be exported to Excel spreadsheet for future use. So going back, we can also view waveform and spectrum for PCC1 and distribution panels, and also available for branch drive. Simulation reports can be viewed by selecting reports and choosing each individual report as before, or basically we can generate the simulation summary. So when I click here, it takes a few seconds, so just wait until it opens. And on the first page, let me make this a little bit smaller. So on the first page, we have simulation summary, so that's the first. Then we have single line diagram, and waveforms and spectrums, and compliance report, and the last 2 pages is the individual harmonic distortion results. On the compliance report, you can see that we don't meet IEEE 519 compliance for the system, and that's that basically we fail meeting harmonic limits on both points. Closing this report, we also have a comparison energy report here that provides the summary of the differences between the 2 scenarios, but I will demonstrate this later. So now that we have computed our simulation of the VFD without any harmonic treatment, let's add a linear AUHF filter to the VFD to see what performance we can get with it. So all we need is to click the breaker symbol on the load branch and open the drive system input data. And what we will do, we will change the drive system to the linear AUHF and click OK. You notice on the single line diagram the AUHF box appears, so now we can run the simulation with the filter. So after calculation is done, we can see current distortion at the VFD load branch has dropped dramatically to 6%. Also the current distortion, voltage distortion on the PCCs upstream has been reduced as well. For example, PCC1 voltage THD is 2.2% and current THD is 5.6%. Selecting reports and opening the compliance report page, we can see that now we meet the requirements for both PCCs for voltage and current distortion. We can continue our analysis by selecting different form of harmonic treatment using a second scenario option. However, before we do that, I will change the operating info for a more accurate energy analysis. So let's change the currency to American dollars, consumption to, let's say, 10 cents per kilowatt hour, and demand for $10. And let's say this particular system works 12 hours per day for 260 days a year, which is 3,120 hours in a year. So I click OK. I want to highlight that it is important that the operating info, any changes to operating info must be done before running the simulation. Otherwise, we would have to create a new simulation or use the second scenario option like we do right now for changes for the operating info to be applied to the simulation. When operating info is updated, we can create a new scenario. So I click project and create scenario. And on the one-line diagram for scenario B appears, the single line appears active, and all data have been copied from the previous simulation. So to demonstrate multiple drive system performance, let's change the drive input data and choose the 8-impulse solution for this VFD. So I click OK and run the simulation. So now with the ability of creating two scenarios, we can compare and do energy analysis for the two proposed solutions. So to view the comparison energy analysis report, we select Generate PDF and click Comparison and Energy Report. So again, it takes a few seconds. Let me scale it down so we can better see the summary. So at PCC2 number 2 section, we can see that, let me explain what we actually have seen. So the column number 2 shows scenario A, which was the original linear UHF, and scenario B is the second scenario, which is the 8-impulse. The last column here shows the difference between two scenarios. So in the PCC2, we can see that the harmonic distortion is quite good with both solutions. However, the energy consumption appears to be higher for the 8-impulse. We should note that the default conditions are perfectly balanced three-phase voltages with no pre-existing voltage distortion. As this rather seldom exists in real life, we will apply some pre-existing conditions. So I'm closing this report and go to the source, and let's apply about 1.5% voltage imbalance. As in many industrial systems, it is very common to measure between 1.5 and 3% of the phase imbalance. So I move the slider about 1.5%, and I click OK, and you notice that voltage source distortion and line imbalance shows 1.5% on the single line. So now we can run the simulation, and looking at the tables for PCC1 and PCC2, we can see that the 18-pulse drive system dropped off the performance, and the THD exceeds 18%. Going to reports and opening, we can see that now we fail recommended limits for IEEE 519 with this solution under small voltage imbalance. So I go back. Also, pre-existing voltage distortion can cause degradation in harmonic mitigation performance. So going back to the source, I can now change voltage background distortion. We have allowed for 5 major harmonic components in the source voltage distortion. So by sliding the indicators, I can set the level of each harmonic in the background. So let's set some numbers here for all 5 harmonics, and so I'm setting up 2.75% of voltage distortion, which is very common in many industrial systems. So now I click OK, and we'll notice 2.75% voltage distortion, and together with the imbalance, and I run the simulation. Okay, so now we see that the performance dropped off even further with the 18-pulse solution. To compare this against the lineator under the pre-existing conditions, we can switch back to scenario A. So I click that switch to scenario A button to go back, and I applied the same source conditions as in previous scenario. So 1.5 voltage imbalance, 2% of the fifth, okay, 1.5 for 7th, and so on. 0.5 and 0.2. So I click OK. I run this simulation now, and performance is much better than with 18-pulse VFDs. And viewing the compliance report, we can see that we still meet all required harmonic limits even with these pre-existing conditions. Having 2 scenarios calculated, we can view the comparison and energy report to compare the 2 solutions. So let's go to comparison and energy report and see again. I will scale it down a little bit. So looking at the energy consumption and energy costs, we can see that significant annual cost savings can be achieved with the lineator AUHF solution. The difference column shows above $5,500 advantage of energy cost per year. The positive sign here on the difference columns indicates that scenario B has a higher number, and the scenario B was the 18-pulse solution. In this case, obviously, if we set the operating runtime for 24 hours and 365 days in a year, the savings will be even higher. So I'm closing right now this report. And now that you are familiar with the scenarios and how to do energy analysis, I will demonstrate what effect a power system source impedance will have on the current and voltage harmonic distortion. So in this case, I load another example file I have prepared before, and we have 3 variable frequency drives and some of the linear loads, 1800 horsepower total power of the nonlinear loads, and they are supplied from 3750 kVA transformer with 5% impedance, which is considered rather stiff source. So I run the simulation now, and after calculations are finished, each drive load branch draws current above 31% THD, and the voltage distortion in the system is below 4%. Please note that the ratio of the short circuit current to the load current, ISC to the I load, is about 50:49.6 to be exact. So let's create a second scenario and change the source, the utility transformer, to the generator, with typical 16% subtransient reactance and 2500 kVA size. So I click OK and run the simulation, and we can see that the current distortion with generator supply is lower, is slightly above 22%. However, the voltage distortion in the system is exceeding 12%. Note that the ratio in this case, of short circuit to load ratio, is just about 10, which is almost 5 times lower than with the utility supply. So now to continue our analysis, I will go back to scenario A and change the utility transformer size to a smaller one, let's say 2000 kVA, and I leave the same impedance, relative impedance, 5%, and let's run the simulation. And we can see that even with the lower impedance utility supply, the voltage distortion increases substantially when the transformer size is decreased to 2000 kVA. Voltage distortion in this case reaches 6.5%, which is a little bit higher than commonly accepted 5% limit. Note that we didn't change the per unit impedance value of the transformer, but decreasing the size of the supply transformer, we affected the short circuit capability of the system, and the short circuit current to the load current ratio, ISC to I load, was lowered from about 50 to 26.2. Therefore, it is important that the actual source impedance and the ratio of short circuit current to the load current is taken into account when doing some harmonic analysis. So this concludes our webinar. Thank you for your time, and now I'm ready to answer your questions. Okay, we have a question. If we consider DC link reactor connected on both positive and negative bars, yes, this is actually for the simulation file. It doesn't make too much difference. This is using mathematical models. So the effect would be rather similar. So we can address that with our developer if there would be any difference, but we're considering that. Okay, another question. File saving menu saves only one scenario. Yeah, we are aware of this, and we think that it's possible, but then we would have to save 2 files instead of 1 file. So again, our developer is aware of that, and we work on this. Okay, another question. This second scenario has 18 poles in series with 6 poles drive. Is this correct? No, this is the model, actual model is 18 poles drive, complete 18 poles drive, and it's just the graphic symbol that's probably not clear showing this. Okay, we have another question. IEEE 519 has THDI limits, but is the priority not the THD volts limits? Well, the intention of IEEE is to lower the voltage distortion, and the latest release has made this a little bit even easier with the voltage, but the reason for current distortion is still the table for the current distortion didn't change, and the reason for the current distortion is that the actual load that's there is not causing a voltage distortion. So the main intent is the voltage distortion, but we need to think what is causing the voltage distortion is the actual load, which is basically current in the system. How close, question, how close does the software calculations meet real test measurements? This is a very good question. Actually, our software is very accurate in this regard. We compare our software to very expensive packages available on the market like ETAP, SKM, or PSpice, which cost over $20,000, and we developed our models based on mathematical calculations, differential equations, and all that arithmetics, but we verified our models with real tests. So, for example, when we initialized SOLV as a software, we corrected our models to reflect real-life application. So I would say that SOLV is much closer to the real tests than any other software on the market. Okay, do we take possible resonance effects into account, load with filter? Yes, and it actually would show, so I can demonstrate. If you, for example, click after the simulation is done, if you click here, you will see waveforms, and these are waveforms on that would be seen on the output of the filter as well here. So you would see that there is some oscillation going on if that's the case. Okay, a few more questions. Will the presentation be available for download? I think we are recording this, so the whole presentation with my voice will be included for download.
Actually, we'll be sending it to everybody who's listening in today. So.
Okay, thank you for correction.
No, just a little clarification.
Okay, a few more questions. Do Mirus filters include capacitors? These create problems with generators. Does Mirus include contactor for opening the filter when on standby power generator units? This is a perfect question. I love these questions because yes, Mirus filters include capacitors, and no, we don't have problems with generators because our capacitor bank is very small compared to any other filter on the market. It's actually 1/3 of the standard passive filter that's on the market. So we don't need contactor for this reason, because the reactive power seen on the input side of the filter is very small if the generator is used, the standard generator, and that can accept up to 20% capacitive reactive power. We'll have no problem with our filter. At PCC2, your report gives a TDD value, but in reality, if this was a utility transformer, it would supply many loads than those only connected to the user transformer. Yes, this is true. However, the TDD value measured at the utility transformer would include all other loads, and there probably would be some other cancellations and reaction with other users. So we only show what these particular loads that we try to simulate for the one customer, what effect of this would be on the utility transformer, regardless of other users. Okay, a few more questions. If we had a large number of drives, can we approximate these by summing up the kilowatt ratings into one larger drive? For example, if we had 20 50 kilowatt drives, can we present in a single line as 1000 kilowatt drive? What inaccuracies will result? Mathematically, this is correct. You can do that. You can multiply 20 by 50 and simulate this by 1000 kilowatt drive. And we verified this in real life, that the simulation result in SOLV will be very accurate, provided that also cable impedances and if there are any power factor correction capacitors used, they are also provided on the simulation as real numbers. Another question, any problem connecting a UHF filter on circuit already including AFE drive, LCL filter interference? We have no feedback of any problems. So far we know our filters work with AFEs on the same bus. So we have no problems reported so far. So I am not aware if there is any interactions. Okay, more questions showed up. Can you go back to other example and look at the 18-pulse scenario? In that example, 18-pulse is in series with 6-pulse drive. Is this configured properly? This was my original question. Okay, so let me try to open that file. And change this to 18-pulse. Okay. Okay, I know what you mean. So this says 6-pulse drive here, but this is 18-pulse. So basically that label here is incorrect. So the whole solution here, the 900 horsepower drive, is an 18-pulse solution, despite the fact that the label here says 6-pulse. Okay, a few more questions. What if linear load as well as VFD constitutes the load after the filter? Okay, what? The linear load after the filter can be moved to upstream for the first line, for the linear load here. So it would be simulated as the load upstream, but for the PCC1 or PCC2, it will have very similar effect as it was on the output of the lineator. Okay, a few more questions. Do system power factor correction capacitors on the main bus have an effect on your filters? Not too much. Our filter is designed with high impedance of the blocking reactor. So technically, there is no interaction between anything that is upstream. There is some effect of harmonics coming to the filter when the voltage distortion upstream is very, very high. High meaning like 18% voltage distortion, then we have some more current going inside the filter. But we have no records of any instabilities in the system or interaction with power factor correction capacitors. Okay, last question. Isn't the IEEE 519 supposed to be measured at the line side of the utility transformer? If that is the case, I would like to see PCC2 on the line side. Would there be much difference on this example if we were on the line side? Okay, this is probably reflecting the latest revision, the IEEE 519 2014. Which defines the point of common coupling on the primary side of the utility transformer. And historically we were using this on the secondary side because our approach was that basically before that PCC point of common coupling was not clearly defined as it is a little bit clearer now. But the reason being is that if the user is causing distortion on its own system, and that can be measured on the utility transformer secondary, it would apply also, or not apply, it will appear also on the primary side. It's just with different ratio of the voltage ratio of that utility transformer. But percentage current THD seen on the primary side in relative number would be the same as on the secondary side.
Great. So that is all the questions. So thank you, Marek, and thanks everyone for your great questions. We hope this has been a helpful explanation for how you can use SOLV to diagnose harmonics. If you do have any further questions, please don't hesitate to contact the team. The contact phone number, email, and website is there. And we will be sending a recording of today's webinar if you'd like to review any details or share it with colleagues. Thanks very much and have a great day.